Okay, here we go. Solution to problem of the day posted on 6/29, which I think was yesterday. Okay, the problem was prove that the covariant derivative of the metric tensor is equal to 0. Okay, so we're going to take the covariant derivative of a 2 times covariant tensor, right? Okay, so here's what's going to happen. Since we've got two covariant indices, we need two negative connections, right? Two negative connections. And we've got 1, 2, 3, 4, 5 holes in each one of these. And there's 3 free indexes here, which have to remain in the covariant position along here. Okay. So that should automatically clue you in that whatever goes up here is going to be a summation index because there are no contravariant indexes. Okay. So the way I always start this, right, I know that if this is negative, the summation index goes upper to lower, upper to lower. So I do that first. So here's my summation index. And then I only got these 3. So I pick these 2 for the first one and those 2 for the second one, and it works out. KI, here's my summation index. J's left over. KJ, summation index, I's left over. So, all right. So now, what is this? Let's substitute the definition of the metric tensor back in that differential, like that, right? It is the dot product of EI dot EJ. All right, so let's do our product rule for differentiation. The first times derivative of the second plus the second times derivative of the first. Okay. Substitute the definition of the Christoffel symbols back in here. These are different. The derivative of a basis vector with respect to a coordinate is a Christoffel, the symbol. So let's take these and write them out as their Christoffel, the symbols, right? And you know how to do that because you've got these two covariant indexes. So all you have to do is keep those straight. Then this becomes a summation index. So now we've got E dot this, E dot that. This remains unchanged. Now we can pull these components outside of this dot product. And it looks like that. Now, what's this and this? Well, this is a metric tensor, right? So we've got defined these dot products as metric tensors, and we got this. Okay, here's the kicker. You realize that by now that the metric tensor is symmetric about its lower indices, and Christoffel symbols are symmetric about their lower indices, right? So when you see a JK, it is the same as a KJ, as that. And when you see an IM, it is the same as MI. So look at that. Now I'm going to rearrange them so they're alike. So this is the same as that, and this is the same as that. And they come out to be 0. Okay? Does that make sense? I'll see you later.